Hello, welcome again. Let us continue with the basic concepts of engineering thermodynamics. In this session, we will define thermodynamic property, state, path, process, cycle, thermodynamic equilibrium, point and path functions, work, temperature, heat, and also we state Zeroth Law of thermodynamics. First, let us understand the meaning of thermodynamic properties. So, what is a property of a system? A property is any quantity which can be used to specify the state of a thermodynamic system, or a property is any observable characteristic of a system. That means it is a measurable quantity. For example, temperature of a fluid can be measured. So, temperature is a property of a system. Similarly, the pressure can be measured. Pressure is a property of the system. Volume can be measured. So, volume is a property of the system. This step, if we have a coordinate system, temperature can be marked on the coordinate system. Or temperature can be one of the coordinates. Pressure can be one of the coordinates. Volume can be one of the coordinates. So thus we can say a property is any observable characteristic of a system, or it is a measurable quantity. So as I mentioned, volume, temperature, pressure, etc. These can be called as properties of a system. Thermodynamic properties can be classified in various ways. One of the ways of classifying properties is as extrinsic property and intrinsic property. What do we mean by extrinsic property? Extrinsic property can be specified with respect to a frame of reference. Let us say there is a reference point. Something like, let us say a point P is moving with respect to this point. So at a given instant, the distance. So this point P is at a distance D from a reference point. So we always measure with respect to a reference. So such a property, we call it as an extrinsic property. Suppose I take a mass, and what is potential energy if I ask? Then the potential energy is given by mgh. M is the mass, g is the acceleration due to gravity, h from which, what is the height from which point? So there is a reference from here. If this is the h, then with respect to this, we can define the potential energy of this mass m. So this is a reference point. This is a reference point like this. So such properties which can be explained or specified with respect to a frame of reference, we call them as extrinsic properties. And those properties which are independent of frame of reference, for example, volume, mass, etc., we call them as intrinsic properties. Thermodynamic properties can also be classified as extensive properties and intensive. Extent, the size. Intensive, independent of the size. For example, extensive property depends on the size of the system, their mass, volume, energy, etc. Intensive property is something, as I mentioned earlier, independent of size of the system. For example, pressure, temperature, specific volume. Volume divided by mass, what we call it as specific volume. Density. So these are all what we call them as intensive property. They don't depend on the size of the system. So these are very important. It is better to remember these concepts. Now, air, many times we use as a working substance. It is better to know air properties, say at sea level condition. Air is basically The gas is a mixture of 78% nitrogen, 21% oxygen, and traces of water, carbon dioxide, argon, and so on like this. So here it has a mass, it has a volume. Let us say what is density? It's a property. Density is represented by rho, and its dimensions are mass by volume. In metric units, its value is 1.229 kg per meter cube. Specific volume, it is volume per mass. So density and specific volume, they will have inverse relationship. It's 0.814 meter cube per kg. Pressure, force by area, 101.3 kilonewton per meter square. As I mentioned earlier, in SI system, it is 1.01325 bar. Temperature, we consider it as 15 degrees Celsius. Similarly, viscosity, 1.73 into 10 to the power of minus 5 Newton second per meter square. It's all measured at the sea level condition. These are some of the standard properties better to remember. I'm not mentioning about the English or FES system units because hardly we use in our course. So most of the times we use SI units. Here I just mentioned the metric units. Let us define some of the thermodynamic properties. Let us say state. What we mean by state? Let us consider this system. Of course, there is some gas in it. It may be air as the substance which is present over here. I have put a boundary and this is the system. I can measure the pressure of this system. Also, I can measure the volume. If I have a coordinate system, pressure and volume, I know what is volume value. I know what is pressure value. I can mark this. This is what I call it as state of the system. Means if you know the properties of a system, we can always define the state of the system. So we say properties specify the state of a system. When all the properties of system have definite values, the system is said to exist in a definite state. Then let us talk about what is change of state. Let us say initially the system value I know, pressure and volume. So I know pressure, I know its volume. So I mark the state. Correct. Now, what I'm going to do is, let us say somehow I change its pressure, keeping the volume constant. Maybe I let out some gas from here and reduce its pressure. So now with that, I know the new pressure value and the new volume value, I mark this point. So earlier it was in state 1, now it is in state 2. This is what I call it as the system has undergone a change of state. For example, you look at this here. There is gas over here. I know its pressure, I know its volume. Let's say I move this up. Now what is happening here, the volume changes. Say pressure also changes. So I know the new pressure value and new volume value, I can mark the change against state. Then I say the system has undergone a change of state. To change from one state to another state, probably I might have to supply heat or remove heat or something like that. So we'll talk about this later. This is only, let us understand I know the coordinates, that is pressure and volume. I mark this. Another, now I make the system undergo some change. So because of that, pressure might change or volume might change, and I get the new values and again a mark. And then we say the system has undergone a change of state. So here, you see here, on the pressure and volume coordinate, it was at state 1 and state 2. In this case, what is that I am doing? I am keeping the volume constant, only there is a change in pressure. So it was at a higher pressure earlier, now it is at a lower pressure. Keeping the volume constant, I have changed the pressure. Here, look here. I know the pressure, I know the volume, I mark the state. I'm keeping the pressure constant, volume has changed. So it is again undergone a change of state. Here I know pressure and as well as volume. I mark the state 1. This system, let us say, experience both change in pressure as well as volume, and later I mark, let us say, state 2. So this both volume and change, volume as well as pressure have changed here. So we say this as this change in or change of state. A system is said to have undergone a change of state when at least one of its properties changes its value. Here, the property pressure has changed, the property volume has changed. Here, the property both volume and pressure have changed. This is what we mean by change of state. This is the equation of state. So, in chemistry and all that, like you must have studied about the ideal gas equation PV equal to RT. So, this is equation of state. So I know properties pressure, volume per mole, and temperature is possible to represent this, right? But in the form of an equation, when we write it as PV equal to RT, this is what we call it as equation of state of an ideal gas. So the state of a system can be represented as a point and a coordinate system, which I explained earlier, with thermodynamic properties as coordinate axis. It is therefore obvious that the thermodynamic state can also be defined completely by an equation involving thermodynamic properties. So I just write in general, function of pressure, volume, temperature is equal to 0. This we call it as simply an equation of state of the system. This one we can represent in various form. One of the form is equal to PV equal to RT. Next, path. Look here, this is the initial state. This is the final state of a system. While undergoing this change, it must have followed a particular path, particular this thing, right? For example, you see here in this, the system has undergone a change of state, keeping the volume constant. Here, keeping the pressure constant. This is what we call it as it has followed this path. During this change of state, the volume is constant. During the change of state, the pressure was constant. Maybe during the change of state, the temperature was constant. Path is a complete series of state. Look here, while going from one state to another state, okay, state 1, maybe it is 1 dash, 1 double dash, 1 triple dash, and so on, and finally it may become state. So one state to another state while undergoing again, this series of intermediate states will be there. Mark all these states and join this point. That's what you will get the path. So a change of state of a system is said to be the process if in addition to the end state, the path of the system is described. What exactly it means? Initial state I have defined, final state I have defined. And also I have said, put the constant that the volume is constant. This I can call it as constant volume process. Isochoric process I can call it. Here you can see that I'm keeping the pressure constant. From state 1 to state 2, in this path, I'm keeping the pressure constant. I can call it as constant pressure process or same pressure, isobaric process, I can call it. Here, from state 1 to state 2, I'm keeping the temperature constant, let us say. So I can call it as isothermal process. Temperature is constant. So a change of state of a system is said to be the process if, in addition to the end states, the path of the system is described. As I mentioned, it can be isobaric, it can be isothermal, it can be isochoric, right? Constant volume. Or there is something like we also define a process called adiabatic process. Later I will explain about this. Right? Now, cycle. I started with state 1. Then this is the path I have followed. Come to state 2. Again I follow this path. I come back to the same original state. This is what I call it as a cycle. A cycle is a process of a system whose end states are identical. What do you mean by initial state was also 1 and final state is also 1? So end states are identical. This is what we call. Then we say the system has executed a cycle. Now let us talk about thermodynamic equilibrium. What is thermodynamic equilibrium? Now let us look at this. I know the pressure value, I know the volume value, I mark this state. So again, there is a small change in volume, small change in pressure. So now, if I can measure the new state, the pressure and volume of new state, I can mark this. Maybe I make some changes in the system. If I again measure the new pressure value, volume value, I can mark this. There is an equilibrium state, then only I can measure this pressure and volume. And again, if there is another equilibrium state, then only I can measure. So then I can mark these equilibrium states. Correct. Each one of them is in thermodynamic equilibrium, we say. What it means? How do we explain this? A system is said to exist in a state of thermodynamic equilibrium when no change in any macroscopic property is registered if the system is isolated from its surroundings. A system is said to exist in a state of thermodynamic equilibrium when no change in any macroscopic property. A macroscopic property can be pressure, volume, temperature, is registered if the system is isolated from its surroundings. Means you take a system, initially you measure its properties, macroscopic properties, and then isolate the system. Once again you measure the properties. So there should not be any change in that. Then we say that the system is in thermodynamic equilibrium with its surroundings. So thermodynamic subject is always deals with the physical systems that are found in equilibrium state. So in other words, let us understand clearly what exactly thermodynamic equilibrium means. We say a system is in thermodynamic equilibrium when it satisfies these three conditions. It should have mechanical equilibrium, it should have chemical equilibrium, it should have thermal equilibrium. For example, let us look at this. I have a system. Let us say the mass is 22 kg. Temperature is 20 degrees Celsius. Let us say volume is 1.5 meter cube. Right. So now the question is, let us say this is not moving, because if the pressure on this side in the surrounding pressure and this pressure both are equal, means there is no pressure gradient across this will not move. Then we say this is in mechanical equilibrium. So there should not be any pressure gradient. That's a very important. The temperature here, both are same, let us say. If they are different, what will happen? Something will flow from here to here. So there is no temperature difference between the system and its surroundings. Then we say the system is in thermal equilibrium. There should not be any temperature gradient. For example, you see here in the system, one place it's at 20 degree, 23 degree, 30 degree. There is a temperature gradient. So definitely heat will flow from high temperature region to low temperature region till it all becomes same. So this is definitely what you can say, it's in thermal inequilibrium. This is in thermal equilibrium. Suppose if this is what I have said, if these two are not in equilibrium, then definitely this will move till the equilibrium is achieved. Similarly, suppose I take a system and no chemical reaction occurs in that, then I say it's in chemical equilibrium. So a system to be in thermodynamic equilibrium, it should satisfy the mechanical equilibrium condition, chemical equilibrium condition, and thermal equilibrium condition. For example, you look at this balance. If both the weights are same, the distances are same, then there is no problem. If the mass of any one of these is different from the mass of this, then definitely what is going to happen? This will start oscillating. So this is what I call it as mechanical equilibrium. Look here, there's a pressure acting on these things, and there's a mass here. So mass and the weight will be acting downwards, and it is balancing. This pressure into area, the force is acting in the upward direction. If these two are equal, then this will not move. Then we say it is in mechanical equilibrium. Suppose if you take two bodies, one is at 0 degree and 100 degree, another one is 100. If you bring them together, definitely something will flow. That heat will flow from here to here. It will go on till both the temperatures become equal. Then we say it's in thermal equilibrium. This is not in thermal equilibrium. This is in thermal equilibrium. Same way, I take like this. If no chemical reaction occurs and all this thing, then we say it's in chemical activity. If there is a chemical potential, definitely a chemical reaction will occur, then it will not be in chemical equilibrium. So, a system is said to be in mechanical equilibrium if there is no unbalanced force within the system or between the system and its surroundings. If an unbalanced force exists, either the system alone or both the system and the surroundings will undergo a change of state till mechanical equilibrium is attained. A system is said to be in chemical equilibrium if there is no chemical reaction or transfer of matter from one part of the system to another part take place. Suppose the system is already in mechanical and chemical equilibrium and it is separated from its surroundings by a diathermic wall, means which allows the heat, and if there is no spontaneous change in any property of the system is said to exist in thermal equilibrium. When the condition for any one of the three types of equilibrium are not satisfied, a system is said to be in non-equilibrium state. So let us talk about a quasi-static process. Suppose, to begin with, let us say this is the system. I know its volume, I know its pressure. I mark this. So then I move this to a next point very slowly. Once again, I know its volume and its no pressure. I go on marking like this. So I can get every time I establish an equilibrium and go on marking these things. So I can either do it in this direction or I can do it in this direction. So every point I have marked is an equilibrium state. But in reality, what happens? All of a sudden, either we open, suddenly we compress. So initially, I have an equilibrium state. Finally, I have an equilibrium state. In between, states are not in equilibrium states, right? But in between states also have to be in equilibrium. Then I have to either compress it very, very, very slowly, or I have to expand it very, very, very slowly. We call it as infinitesimally slowly. Then only I can mark those equilibrium states over here and I can draw this line. If the in between states are not in equilibrium state, I cannot mark that line. So this is a spontaneous process. This is not a spontaneous. Very, very slowly I'll take out. I call it as a quasi-static, almost a static process. So to simulate this quasi-static process, what we do, suppose, let us say initially I have a state like this. I know its pressure, I know its volume, I'll mark this state. Assume that I have a weight, slices, that big weight, I have converted to slice, like cucumber slice, you can say, like very, very, very thin slice. I take out one slice, then it will attain equilibrium with its surroundings, measure the new pressure and volume, mark the state. Then I take out another slice, very, very thin slice, and there will be a change in state. Then it will attain equilibrium with the surroundings. I measure it. So these are all equilibrium states. I have to maintain this equilibrium state, means I have to make this process should be carried out infinitesimally slow. So this is what we call it as a quasi-static process. But in reality, it is difficult. Whatever happens is spontaneous. Because to perform any analysis, perform calculations and all that things in thermodynamics, we need these equilibrium states. Correct. But this is what really happens in actual case. Then we can compare the actual one with the ideal one. Ideal one is almost the quasi-static process. In thermodynamics, we use the word point function and path function. Look here, this is the initial state of the system. I know its pressure, I know its volume. I can measure it and mark a point. Then I make the piston move to this position, again infinitesimally slowly, and go to this position. Again, I measure its pressure and volume. I mark this point. Correct? This is why we call this as something like, no, these are the properties. Pressure, I know, volume. Again, pressure, I know, volume. I can represent this by these points. So thermodynamic properties like volume, temperature, pressure, etc. are point functions, because a name arises from the fact that for a given point on a coordinate system, the state is fixed. Thus, there is a definite value of each property corresponding to this point. So what is the change in volume in this case when the system has undergone a change of state from state 1 to state 2? I can simply write integral of dV, and I can write V2 minus y, V2 minus V1. I can use definite integral 1 to 2 dV. I can simply write V2 minus V1. So a quantity which is path independent is a property of the system. It is point dependent. Suppose while undergoing this change of state, the system must have gone like this, or gone like this, or gone like this, immaterial. So it is not depending on the path it is following. It is simply depends on the end states. Like that's such a system, we call it as point function. All point. So a property is always a point function. So volume is a point function. Volume, pressure, these are all properties. We call them as point functions. And change in pressure, change in volume, change in temperature, we can always find out using definite integrals. Now let us consider something. Again, there is a state 1 here, state 2 here. The change of state can happen following this path, or following this path, or following this path. Suppose I want to find out what is that value. The value, let us say the value depends upon the area under the curve. Suppose I follow this path and this is the area. Suppose if I follow this path, then this is the area. So that means the area under this curve is something. We will call that something later. Maybe it's work or maybe heat. We call it later. They depend on path. They don't depend on end states, like these points end states. Depend on the path they follow between the end states. So such a quantity which is path dependent is not a property of the system. We call it as path function. You cannot determine by exact differentials. There is inexact differentials. Suppose, as I said, this quantity, maybe the area under this can be work. Suppose pressure unit is Newton per meter square. This is metric cube. If I multiply, it is going to be Newton meter, which is nothing but the unit of work. So suppose if I followed this path and the area under this is can be work. So if a system undergoes a change of state by following this path, whatever work is done during that state is different from the work done if it follows this path. And this is again different from this, if the system follows this path. So that way it is not depending on end states, but it depends on the path it follows. Such a property, such a thing, we can call it as path function. Path is not a path. A quantity which is a path function is not a property of the system. For example, as I mentioned, like this area, this what I said, work is a path function, is not a property of the system. Similarly, I can draw with different coordinates and I can find out the heat. The again heat depends on the path the system is going to follow. So again, heat is also going to be a path function. Since it is a path function, heat is also not a property of the system. So work and the heat, these are path functions and they are not properties of the system. Look here. On the other hand, the magnitude of some interactions like work, heat, which will be dealt later, depend on the path followed. The differentials of path functions are inexact differential. That's why we represent like this, delta. The symbol D is used for exact differential and delta is used for inexact differential. So path function, a quantity which is a path function is not a property of the system. A quantity which is a point function is a property of the system. Property means they depend only on end states. Not a property because they depend on the path the system follows while undergoing a change of state. This is a concept of continuum, how big the system should be or how small the system can be. So there is a lump of gas and just say this is my system. So in this system, how small the system can be or how big the system should be. From the macroscopic point of view, we are always concerned with the volume, which are very large compared to molecular dimensions. Suppose I choose a system very small, smaller than the intermolecular distance, then inside the system there will not be anything. Then all my concepts, like whatever the definitions I was talking about, all fail. So even a very small volume of a system assumed to contain large number of molecules so that statistical averaging is meaningful and its property value can be assigned to it. Disregarding the behavior of individual matter is here treated as continuous. The concept of continuum loses its validity when the size of the system is smaller than the intermolecular distance. Okay, what exactly I mean by the word continuum? So continuum means matter is made up of atoms that are widely spaced in the gas phase, yet it is very convenient to disregard the atomic nature of the substance and view it as a continuous. That is, matter is continuously and uniformly distributed within the system. Suppose if I choose the system in such a way there is no matter in it, no molecules at all in that, then there is no, the concept of continuum will not work there. Sometimes what is this thermodynamics, what is this thermostatics? So be clear now, whatever we study is study in the systems are in thermodynamic equilibrium. That is, the science of thermodynamics deals with the system existing in thermodynamic equilibrium states, and these states are specified by the properties. So this has to happen, the process has to undergo infinitesimally slowly. That is, infinitely slow quasi-static process executed by the system are only meaningful in thermodynamic plots. If I don't assume that, it is not possible to draw thermodynamic states and the thermodynamic, plots. That is, suppose on the PV coordinates, if I have a series of thermodynamic equilibrium states, then only I can join them and I can obtain the plot. The name thermodynamics is said to be misnomer since it does not deal with the dynamics of heat, which is a non-quasi-static, that is thermostatics. So most of the real processes are dynamic and non-quasi-static, although the initial and final state of the system might be in equilibrium. Such process can be successfully dealt with by the subject, hence thermodynamics. In thermodynamics, thermostatics refers to the aspects of thermodynamics concerned with thermodynamic equilibrium. Thermostatics is sometimes synonymously used with the thermodynamics of equilibrium, or we call it as equilibrium thermodynamics. Let us talk about the idea of the property temperature. Look here, suppose if a hot and a cold body are brought into contact, then something flows from hot body to cold body. That something decreases the hotness of hot body and warms up the cold body. So however, the idea of hotness or coldness is relative. For example, let there be two bodies having different but higher hotness as compared to the observer's fingers. Let him first touch the hotter body and immediately after it, the second body. The second body will appear to be cold to him because the hotness of the finger has changed during the first process. These facts necessitate the existence of something which can express the hotness of the body. This something is a property of the system and is the central idea of temperature. Correct? So, if the temperature is very high, we say it's hot. The temperature is low, we say it's very cold. Correct? So, this is something which determines the hotness or coldness of a body. Look here, suppose I have this thing, right? One body is a cold body, another is a hot body. I bring in these two in contact, then something starts flowing from here to here, and till something remains the same in both the bodies. This is what I call it as the temperature, something that flows from here to here. This is what we call it as a heat. To understand the principle of equality of temperature, consider a body at high temperature being brought in contact with another body at relatively low temperature. This causes heat to flow and in turn to change the various physical properties, example, volume, electrical resistance, etc. The decrease in most of the properties occur in hot body and the reverse in cold body. This continues till a limit is reached, after which there is no change in these properties. That's what we call it as, then the system is in thermal equilibrium. Okay, so a property which determines a given body is in thermal equilibrium with other body or not is what we call it as temperature. This led to the statement of Zeroth Law of thermodynamics. So, how do we state the Zeroth Law of thermodynamics? Two systems in thermal equilibrium with a third or in thermal equilibrium with each other. Let us say there is system A, system B, system C. This I call it as a diathermic wall. This I call it as an adiabatic wall. What is diathermic wall? A diathermic wall is one which allows the heat to flow across it. Adiabatic wall is one which will not allow heat to flow across. So these two are in thermal equilibrium, these two are in thermal equilibrium. So if I take out this adiabatic wall and bring a diathermic wall, definitely there is no exchange of heat. This already have attained thermal equilibrium. That's why we say two systems in thermal equilibrium, two system. This is A is in thermal equilibrium with C, B is also in thermal equilibrium with C, or in thermal equilibrium with each other. So I take a thermometer, I measure the temperature of body A, let us say it is 40 degrees Celsius. Then I measure the temperature of the body B, that is also 40 degrees Celsius. Then thermal equilibrium with each other. So that is what we call it as Zeroth Law. So from Zeroth Law, we say leads the the property temperature, right? Arises. Like temperature is a property. It is a result of Zeroth Law of thermodynamics. Sometimes we have to measure this temperature. So for that, we use a device, a thermometer. So inside this thermometer, maybe, or for the thermometer, the temperature to be measured, a property of the material that we use for the measurement of temperature is important. That is what we call it as a thermometric property. So what is this? In order to obtain a quantitative measure of temperature, a reference body is used, and a certain physical characteristic of this body which changes with temperature is selected. The physical characteristic can be change in volume, it can be change in pressure, it can be change in temperature, it can be change in EMF, anything like that. That physical characteristics is what we call it as thermometric property. So based on this thermometric property, we can have different types of thermometers. What are those thermometers? Constant volume gas thermometer. Means you take a thermometer, there is a gas and its volume is constant. So initially I measure the temperature of a gas, let's say. So it has volume, it has certain pressure. Then I'll just dip this thermometer into a hot body. Since the volume is same, when the heat is transferred to this gas, its pressure will increase. So the difference in pressure or change in pressure is what indicates the temperature of the body. So pressure becomes the thermometric property. Similarly, I can have a constant pressure gas thermometer. So here, keeping the pressure constant, as the temperature changes, volume can change. So volume I can use as a thermometric property. Pressure is directly proportional to temperature and the volume is kept constant. Charles Law. Pressure is directly proportional to sorry, sorry. Volume is directly proportional to temperature when the pressure is constant. Again, Charles Law. So using this idea, we can develop thermometers. Similarly, electric resistance thermometer, change in resistance. When the heat flows to a body, the resistance might change. EMF might change. Then I can call it as a thermocouple. So mercury, here length can change. That is what the length becomes the thermometric property when I use mercury in glass thermometer. So I hope you understood the meaning of thermometric property. Thermometric property, as I mentioned, is a physical characteristics of the body which changes. And when the heat flows into it or out of it, and because of that, the characteristic change, and the change in characteristic can be used for the measurement of temperature. Now the thing is, initially there is certain volume, let us say, and certain pressure. Let us say it is a constant volume thermometer. Then I dip this in a hot body. Its volume remains constant. It will indicate different pressure. So how exactly we relate this new value of pressure with new to determine the temperature of these things? So I must have a scale, correct? And this scale should be standard, accepted by all. So now the thing is, so for that reason, we need to calibrate this kind of thermometers. For calibration, we require certain standard points. So ITPS, International Temperature Scale, these are all the calibration points that we use. Normal boiling point of oxygen, this value is minus 182.97 degrees Celsius. Triple point of water, 0.01 degrees Celsius. Normal boiling point of water, 100 degrees Celsius. Normal boiling point of sulfur is 444.60 degrees Celsius. Normal melting point of antimony, 630.50 degrees Celsius. Normal melting point of silver, 960.80 degrees Celsius. Normal melting point of gold, 1063 degrees Celsius. Now let us say I want to use a resistance thermometer to measure the temperature from the range of 60 to 650 degrees Celsius. Resistance is given by R is equal to R naught 1 plus AT plus BT square. R is the resistance at any temperature T. In this equation, there are three unknowns, R naught, A, and B. If I know R naught value, A value, and B value, then I will have a relation R is a function of temperature T. In a new case, when R is known, I can calculate the temperature. So how exactly we find out the values of R naught, A, and B? To find out these three constants, I require three equations. How exactly we compute this? R naught A and B are computed by measurement at the ice point, steam point, and sulfur point. In this equation, look here, measure R value by dipping this resistance thermometer in ice point. What is the ice point temperature value? 0.01 degree. Put here 0.01, 01 here. I know the resistance. Measure the resistance. I get one equation. Next, steam point. Put 100 degrees Celsius here, 100 degrees Celsius here. Measure the resistance. I'll get second equation. Sulfur point. Sulfur point 444.60. Measure the resistance. Put that 444.60 here. So I got three equations. Solve these three equations. Get the values of R0, A, and B. Then you have equation R with known value of R0, known value of A, known value of B. Now use the thermometer for measurement of temperature. So if you know the resistance value, by solving this equation, we can always obtain the temperature value. So this is what we call it as simply a platinum resistance thermometer. And the diameter of the wire must lie between 0.05 to 0.20 millimeter. And this is the equation is used for calibration purpose, and such thermometers we can always use to measure the temperature range from 0 to 650 degrees Celsius. Suppose we want to measure from lower temperature -190 to 0 degrees Celsius. Then same platinum resistant thermometer is used. Now here, this is the calibration equation. Now to R0, A and B, as same before, means get those kind of a thing. There is one more constant. Oh, that's missing in my equation. See here. So this is determined from the measurement at the oxygen point. There are four equations required. There are four constants here: R0, A, B, and C. This should have been C. Yes. Now suppose you want to measure temperature from 660 to 1063 degrees Celsius. Then I use thermocouple. Here, the EMF generated, that will give you the temperature. There are two dissimilar materials. This is what we call it as a hot junction. This is what we call it as a cold junction, right? So now the question is, when we heat this, like bring in a hot junction in contact with this high temperature, and probably the cold junction in the maybe ice you have to maintain, then it will generate an EMF, and this EMF will indicate the temperature. For that, we need to calibrate this thermocouple. The equation that is used is E equal to A plus BT plus CT square. There are three constant values, A, B, and C. This has to be determined. So these have to be computed, means by solving these equations, by considering antimony point, silver point, and gold point. And while forming this thermocouple, we should use the wire diameter should be around 0.35 and 0.65 millimeter. Okay, so one of the wires is made up of platinum, another one is made up of 90% platinum, 10% rhodium. Two different metals, metal 1 and metal 2. Suppose we want to measure much higher temperatures, then we use radiation parameters. This is how the temperature can be measured. So now, so the idea here is, in this session, I hope you have understood the meaning of thermodynamic property, intrinsic property, extrinsic property, intensive property, extensive property, and all that. What is state of a system, and how do we represent on a coordinate system? What we mean by path, what we mean by process, what we mean by cycle, and the meaning of thermodynamic equilibrium. A system to be in thermodynamic equilibrium itself or surroundings, it should satisfy the conditions of mechanical equilibrium, chemical equilibrium, and thermal equilibrium. And you have understood the meaning of point function and path function. A property is a point function, and a quantity which is a path function is not a property of the system at all. Thus, work and heat are path functions. But anyway, I will further explain in the next session. They are not properties, but temperature is a point function, a property. Then temperature is a consequence of zeroth law. So we have stated zeroth law of thermodynamics, and the consequence of that, as I mentioned, is the temperature. And how do we measure temperature? From in different ranges. What are the different? What is thermometric property, and how a thermometer can be created and calibrated and used for the measurement of temperature. All this we have understood. So hope you go through all these things and get all the concepts clear. Thank you very much.